Hi, my name is Panya from SOICT from Hanoi University of Science and Technology. Today, I'll attempt to give you a very short introduction about naive Bayes classifier in a theoretical mathematical ways. We'll go through four parts. They are what is Bayes classifier and how this called the optimal classifier. Then we will go through naive Bayes classifier, our main topics, and we will dive into two major parts, two major implementation for naive Bayes classifier for discrete input and for continuous input. First, I'll talk about Bayes classifier. Notice that we are working with classification model problem. Consider the dataset D of pair A X I and Y I. X is feature space, Y is a set of all labels. Suppose that we have already known the distribution of x and y, and we want to approximate this distribution p. And so the Bayes classifier is defined that we will take the y that give the maximum. We'll take the y that have the maximum likelihood of y given x. It's easy to see that y is optimal because we're taking the maximum one. But in reality, in practice, it cannot be obtained. We cannot find such a classifier because we don't know the actual distribution. We don't know. So this is just the theoretical classifier. In reality, in practice, we want to approximate this classifier, and naive Bayes classifier is one way. Uh, we can rewrite the formula using Bayes' theorem like this, and as you can see, py and p's of x given y, we can use in reality we can use LME or map to estimate this. P of y is really easy. P of y is quite easy, but this term is the one that makes things hard. In practice, it's really hard to estimate this. Let's make an example. Suppose that we have the dataset of d-dimension binary features, which means just 0 and 1, and we have C labels. So the total number of data that we need to train our classifier is approximate C to the C, this term. As you can see, it's increasing exponentially to the number of dimension, which means really fast, and the number of data that we need might be really large in practice. And in order to fix it, in order to try to go through this difficult, we have naive Bayes classifier. Naive Bayes classifier is one of them. And what is naive Bayes classifier? First, we have to make an assumption. All machine learning model makes an assumption, and in this one, we make assumption that in our data set, in our data In data from feature space, features are independent to each other, which means that the p of x given y is just the product of p of x I given the label. This is the feature of the vector x, the ith features of vector x. We will take the product of all the likelihood. And this makes the computations much more simpler. And from exponential relation of total number of data that we need, from exponential relation into linear relation. This makes things linear. So substitute this assumption into our Bayes optimal classifier. We can have the definition of naive Bayes classifier like this. And with the eyes of computer scientists, we often write it like this. We're using log function to make the actual computation simpler. Okay, now we will go into how to estimate the p of y. Let's just call the pi c is the parameter of this likelihood. Okay, this probability. Just call pi of c is this. So we want to estimate pi of c, right? There are two main ways that we can do it. It's called LME or map. LME is just you take all the data point that has the label C divided by the total number of data that we have. Just really simple. Map, on the other hand, we will plus some number here in order to not overfitting, and we also plus this term in the denominator. And this technique is also called Laplace smoothing. This technique is much more easier to explain than map. Using map to obtain this formula is really hard. It's not really hard, but it's really complicated in such a way. And for p's of x given y depends on, as we said before, as we said at the beginning, depends on the data type. We have two general approaches for the estimation. First, we will dive into how we do it with discrete input. We will call the parameter like this. The theta of ijc is just the probability of the ith feature is equal to j given the label c. Okay, and because of it, we assume that each feature is taken from a categorical distribution. That's why it also called categorical features. The feature is taken from categorical distribution. So we can estimate it. Using LME or map. Right? Map also called Laplace smoothing. Just add some number here and here to prevent overfitting. But it's okay to use this in practice, it is just recounting all the data points that such that the I feature is equal to j and is at a label c divided by total number of data that have a label c. Yeah, really simple. And substitute all of that, we have the distribution for categorical feature naive Bayes classifier with this. Um, we will talk. I want to talk about the application of categorical naive Bayes classifier. It's often it's often used in text classification. Two simple model that we often learn is Bernoulli event model. If Bernoulli event model. It actually is naive Bayes classifier with binary features, just 0 and 1. For example, like spam or ham classification. Um, the other type is multinomial event model. It had a more familiar name, multinomial naive Bayes. Keep in mind that multinomial naive Bayes is just the different name of multinovel event model, which is one type of categorical naive Bayes classifier. It does not mean that the features our feature is taken from the multinomial feature distribution. Let's dive into these things. First, we will rename our dataset. For the text classification problem, we often call this this is how we often call our data set. We have the document with a label, okay, the document 1 with label C1, and etc. And we will expand this set. The asterisk uh, is written like this. The document D1 has the word, the first word, the second word, the third word, and the n1th word. We expand it all. Keep in mind that there's actually no bracket in this. In reality, I just write this for you to easier understand that we want to expand the set D. Okay. So we like before, we call the parameter theta because like a categorical feature, because multinomial is just one of them, so we also call the parameter like this, but the estimation has a change. We count all the words in the document that have a label C, all the words divided by the total number of words that have the label C. Okay. When you use the set D anymore, we use the set D asterisk. And this will have we emphasize on the frequency of the word, right? So it's better than the categorical traditional one. And uh, this is what we often think about when someone talk that they will reference you, will talk to you about naive Bayes classifier. They often refer to multinomial event model. It's kind of misleading name, but uh, which we use it, the community uses it, so we keep using it. And and let's get back to what we start. And as you can see, the order of the word is not important at all. We just care about the word itself with the label, how many times it happened. It doesn't depends on the position of the words anymore. So we can rewrite our parameter like this, and in practice we can use the technique called bags of words. With f of I is the frequency of the word wi, we can obtain this formula. Wi is just all the word in the document we want to test. And we will go right into the final part, is how we use Naive Bayes Classifier for continuous input. And of course, the rules of thumb how to deal with continuous inputs that is that we divide it into multiple buckets, right? We turn continuous input into discrete input, right? But there's another way. There is another way. It's called Gaussian naive Bayes. Let's just assume that all our features given the label C, is taken from the normal distribution of two parameter, the mu and sigma, like this. Right. Each features given the label C is taken from this normal distribution. And the estimation part is I have shown you. It's not really hard at all. It's just using LME, you know. Just add the things that have a label C with the given in the ith position, divided by the total number of data that have the label C. That's how we estimate mu, and similarly, that's how we estimate the sigma, the standard deviation. And please keep in mind that we actually can use any continuous distribution. We don't have to use normal distribution. We choose normal distribution because in reality normal distribution happens a lot. In the end, I want to share with you a very interesting fact that Naive Bayes classifier with binary feature is just linear classifier. The actual formula can be rewrite like this with a lot of transformation. We can obtain this, and you might notice that this expression is really similar to logistic regression expression. Their formulas really looks alike, really similar, but there's a difference. The main difference is the Gaussian. Sorry to have not. Sorry because I have not tell you that logistic regression is used for like continuous. So we will compare it to Gaussian naive Bayes. Okay, we'll compare these two, and the main difference is the naive Bayes classifier is generative model. Okay, is the generative model. It's not. It don't calculate the piece of y's given x directly. It uses Bayes' theorem to calculate the piece of x given y. Not this. We don't calculate this directly, as I have represent before. As I have represent. But the logistic regression, on the other hand, is discriminative model. Discriminative model is try to estimate this term directly. So uh, although they share the same formula, the meaning of the parameter uh, in this formula is different. And that's all. Thank you for your listening. This is the end of my presentation.